that very often. Flash desorption, nowadays people, almost nobody do this anymore because it requires very precise and very good mass spec to pick out your peak. Mass spec just cannot run so fast. People normally do that, do this way because you can control your heating rate. And the heating rate usually run from 15 seconds to a minute or 2 minutes. Usually that's in terms of second to minute. So you can really control in the space of, depending on how much temperature you want to raise, like maybe 800 degrees C or something like that. Usually it's under 1,000 degrees C when you do this temperature. You can measure these type of things. And the advantage of using not just a pressure gauge but a mass spec is that you can measure individual component of your gas. So it could be CO or N2, depending on what you absorb on the surface. You can really do a lot of analysis chemistry, what dissolved that come off from your surface by looking at these mass spectrum of the gas that come off. Okay. And so here is a total pressure measurement. Okay, so here we are looking at the Red Hat analysis that we are talking about. That here different curve correspond to different initial coverage. Okay, so you can see the different initial coverage. And what I'm plotting here is the total number of not the desorption rate, but the total number, because it will be kind of like the flash desorption that you see. It will rise up and then to some area. And what you see is that as N0 increases, the curve shift down this way. Okay, down this way. So to get the heat desorption rate, all you have to do is to take the derivative of this curve. Right? As you take the derivative of this curve, you will get a peak, right? So you get a peak here, and then you get another peak here, and then you get another peak here, because you are taking the derivative of this number. So that's what you see in the desorption rate as you go through. So here, so this three curve corresponds to second order, because we say that the desorption maximum is decreasing with increasing surface coverage, and these two curves compare the shape, general shape of first order and second order. Usually, just said that in first order, the slope of these curve rises are different. Okay, so that's all you have to sort of recognize that they are different. If you're comparing first order and second order, they look different. And in this case here, if you're looking at first order reaction, the curve look quite different from the second order. The second order tends to have parallel type total curve, and whereas here you don't have a parallel type flow curve. But they all give you the same, same desorption maximum, right? As we showed before, like this. They all have this desorption maximum, whereas in the second order is going down with surface coverage this way. Okay. So this is the total pressure, and this is the desorption rate. Okay, so they are plotting to the derivative of this curve give you this curve, and you will see that they are independent of N0. And Red Hat analysis, as we tried to show before, started in 1962, way back. Red Hat retired from NRC about 10, 20 years ago now. He was recognized to be one of the pioneers in vacuum sciences before surface science became popular. And so NRC has a rich history in Ottawa. Is one of the key contributors to surface science. Is in fact Bob Red Hat. He's the guy who gave us this. Still being used quite a lot if you're doing thermal desorption. This is a common thing that people do. And the thing that I alluded to earlier is that the Red Hat analysis eventually give you this desorption energy, which people try to equate between. So the notation that I shown in the previous few graph, delta H desorption is like ED, and his final analysis showed that ED is somehow related to And sometimes this is not quite right, and it's dangerous to use this type of analysis. Okay, so I will ignore this for the time. Okay, so you can, but the line shape is still okay. You can look at the line shape here that we started talking a little bit about. And the line shape for first order is asymmetrical, whereas the second order, x here is the order of the reaction. In this case, x is order of reaction, order of desorption. Same as n that we used earlier. And you can just compare the line shape that you see. And here's a little bit more example that I show as you change the desorption rate, the flux, what happened to it. And one of the interesting thing that you can see is that all this desorption state, all this peak that you see, you call it desorption state. And it's a rich chemistry that you can get out from thermal desorption, because you are heating your surface and you are promoting surface reaction as this occur. And if you have a mass spec, you can look at what is the gas composition of that dissolved gas that from your surface look like. There could be differences. I mean, there could be product coming out, or it could be the original reactant that come out on your surface. So if you can analyze that gas that come out and look at when it come out as a function of temperature, that can tell you how strongly that gas absorbs on your surface, and what kind of reaction that could occur. So here's a little bit of an example of adsorbate interaction between an adsorbate and a co-adsorbate. They have two gas on your surface, and all I want to show here is that the desorption peak are different. Okay, so if you have adsorbate, co-adsorbate interacting with CO in this case, your peak could be very different, and that is due to surface chemistry. So TBD is being used a lot in this sense in the early days in terms of doing this. And unfortunately, nowadays people don't do a lot of TBD because it's a technical difficulty in terms of measuring the temperature. Because when you show me the temperature, I assume that you know the temperature of the surface itself for the gas that come up. And oftentimes, this is not so easy to do. And people do a lousy job in the past in doing this. And you get very big error. But it is very essential for chemists that can do this. Okay. Next. We like to talk a little bit about, similar to TBD, thermal desorption. You don't need to use heat to dissolve your material. You can use other fancy things. You can perhaps use an electron beam to excite your surface or your adsorbate, or you can use a photon to excite your adsorbate. So the difference between electron and photon excitation is, of course, the resonance process, right? In the case of photon excitation, the photon has to be equal to your differences in the electronic state that you're talking about. In the case of electron excitation, you don't need that because you are just transferring kinetic energy in a continuous way, not a quanta kind of way, to your surface. So it's more flexible with the electron beam. But then the difference here is that, of course, the electron beam has momentum. It means that you could have sputtering effect on the surface, and it could destroy the surface itself. So here the picture you have, sometimes this is known as the Mansell-Goldman Red Hat model. Again, Red Hat had contribution to ESD, electron stimulated desorption, and photon stimulated desorption. And the picture really is just that you have